Okay, so we're going to finish up our discussion of Chapter 8, Positional Tolerance, with Part 2 of our presentation. And we're going to look at some of the topics that are discussed at the end of the chapter. All right, and we're going to start off with the concept of bonus tolerance. Okay, so bonus tolerance is any additional tolerance that's gained through the use of an MMC or an LMC modifier in a geometric tolerance. Because we can only use MMC and LMC when we apply our geometric tolerance to a feature of size, this is the bonus tolerance. The bonus tolerance is limited to geometric tolerances applied to features of size. Okay, notice it also does not include the RFS, or regardless of feature size, modifier. So it's only MMC or LMC, only applied to features of size. So that also rules out form tolerances that have no datum reference and are applied to surfaces or features, non-size features. All right. And basically, the bonus tolerance is the difference between the produced size and the MMC size. Okay, the produced size is the size of the hole or the feature that is as it's manufactured. Okay, and the MMC size, of course, is taken from the drawing and the dimensions on the drawing. We have two equations that we can talk about. Really, they're the same equation. All right. The first equation for bonus tolerance is for negative features. Remember, a negative feature is like a hole or a slot. All right. And the bonus tolerance equation is the produced size minus the MMC size. All right, and that's going to give us our bonus tolerance. When we switch and look at a positive feature, and the positive feature again is, one way to explain it is something that you can touch. So like a cylinder or a tab, a notch, something like that, something with thickness. The positive feature bonus tolerance equation is the MMC size minus the produced size. Now notice I put these in color so that you can clearly see. All we're doing is just reversing the terms here, right? And the key is the bonus tolerance always needs to be a positive number. That's the only thing you got to remember. If you get a negative number, provided you're not doing a math error, you just need to reverse these terms. Okay, so if you're worried about remembering which side, which goes first for a negative or positive feature, don't worry about it. Just remember that it's the produced size minus the MMC size, and you always want a positive number. So if you get a negative number and you do the math right, reverse the terms and take the negative off. Okay? Now let's do a couple of examples here. And the first example we're going to do is for a negative feature size, in this case for a hole. So we have a plate here with two holes in it. Don't worry about the datum, that's not important. But we see the dimensions for the holes. Both holes have a dimension of a size of 0.515 plus 5 thou minus 1 thou. Okay. And we have a positional tolerance on both of these holes of a 0.014 or 14 thousandths allowable error at MMC. So at the maximum material condition for these holes, that is the tolerance, the allowable positional tolerance, 14 thou. All right, so let's go ahead and go through the steps to get the equation, find the value for bonus tolerance. The first thing we want to do is get down all the givens. Okay, so first, what is the MMC size of these two holes? Right, the MMC size is 0.515 minus 1 thou. It's the smallest hole size, or 0.514. The positional tolerance is given to us right in the feature control frame. The positional tolerance at MMC is 14 thou. And we can calculate the virtual condition. For a negative feature, the virtual condition is the size at MMC, 0.514, minus the positional tolerance at MMC, 14 thou, which gives us a virtual condition of ½ inch. All right? So, if a hole is produced at 0.517 inches in diameter, what is the bonus tolerance? Well, we know that the equation is the bonus tolerance is equal to the produced size minus the size at MMC. The produced size right here is 0.517. The size at MMC is 0.514. So the bonus tolerance is 517 minus 514 equals 3 thou. So our bonus tolerance for a hole produced at 517 is 3 thou. What is the allowable tolerance then? All right, so the allowable tolerance is basically the geometric tolerance for that produced feature. And that's going to be equal to the tolerance at MMC plus the bonus tolerance. The tolerance at MMC is 0.014, 14 thou. The bonus tolerance, well, we just calculated that at 3 thou. And so the allowable tolerance is 14 thou plus 3 thou equals 17 thou. Another way to calculate allowable tolerance is the produced size minus the virtual condition. The produced size is 517. The virtual condition is a ½ inch. And so the allowable tolerance is 0.517 plus a ½ inch equals, whoops, that should be minus. I'm sorry. That should be minus equals 0.017. Okay. Another way to look at this, and this is the way that I've done in some of the examples, is to just create a table, right? It's a little bit more work than just doing the equations, right? But the table, you can kind of see everything. So the first number in the table, the first column is the size of the hole, right? And we start with the MMC size, 514, right? And then we go all the way through to the least material condition size of the hole, which is 520. That would be 515 plus 5 thou, right? The tolerance at 514 is given to us at 0.014, 14 thou. And the tolerance, notice, as the size changes, the tolerance is going to change by an equal amount. So if we increase the size to 515, we increase the tolerance by 1 thou. All right. So if we produce a hole at 517, what is the tolerance? 0.017, right there. Okay. So there's a few ways to calculate this, right? And you just have to get comfortable with using one way. Whichever way, you have the most confidence that you can make these calculations. Let's look at another example. And in this example, we're going to look at a positive feature of size. So we have an assembly. We have two parts here, right? These are two separate parts. And we're going to look at the cylinder. This is a cylinder right here. On the part on the right, the coupling. Now, I do want you to notice, right, and I did this on purpose, we're looking at the bonus tolerance calculation for a feature that is controlled with a perpendicularity tolerance. So this just goes to show that you don't just need positional tolerance to calculate bonus tolerance or allowable tolerance, okay, any feature of size. So here we have a cylinder, a feature of size. The size of that is 50 millimeters to 49.97 millimeters, and we have a perpendicularity tolerance of 3 thousandths of a millimeter at MMC. All right, so let's do our givens. The MMC size for this cylinder is its maximum size, which is 50 millimeters. The positional tolerance at MMC is given to us in the feature control frame, and that is 30 thou millimeters, right? Or 0.003 millimeters. It's kind of weird to say thou with that. And then our virtual condition for a positive feature is the size at MMC plus the tolerance at MMC. So the virtual condition is 50.03. Okay? So let's calculate the bonus tolerance now. If the shaft is produced at 49.97, right? So if we produce the shaft at its smallest allowable size, 49.97, what is the bonus tolerance that we get? Well, the bonus tolerance is the MMC size minus the produced size. Remember, we want a positive number for the bonus tolerance. So the MMC size is 50. The produced size is 49.97, so the bonus tolerance is 30 thou. All right, 0.03 millimeters. We can go on now to calculate the allowable tolerance, which is the MMC tolerance, in this case 0.03, plus the bonus tolerance, which is also 0.03. So the allowable tolerance is 60 thou. If we produce a cylinder at 49.97, we have a 60 thou allowable tolerance there. To calculate the allowable tolerance is produced size minus virtual condition. In this case, the allowable tolerance would be the produced size is 49.97 minus the virtual condition, which is 50.03, gives us an allowable tolerance of 60 thou, same as the other one. Okay. If you like the idea of using the tables to do these calculations, there's your table right there. So we start at the MMC size and we go all the way to the LMC size, least material condition size. The tolerance changes as we go, right? So we start at 50 and 0.03, that's given. And as we decrease the size of our cylinder, the tolerance increases by an equal amount. And there's our bonus tolerance and allowable tolerance right there. Okay. So let's continue on with a look at how to deal with counterbored holes or compound holes, holes with different diameters. Okay. So there's three methods to control the position of a counterbored hole. All right. The first two, number one and number two, are definitely the most common. But we have three options to cover the whole range of variability here. Okay. In all cases, the counterbored hole acts independently of the other hole, of the main hole. The holes, the centers of the holes, are free to move in opposite directions. Okay? So we're not talking about linking the counterbore hole with the through hole or the primary hole. So in both cases, the counterbores can move, the holes can move independently. All right, so in method number one, we just use one positional tolerance. Okay, and you can see that here in the dimension call out. We have the dimension for these four holes, 4 times diameter 380 to 395, counterbore diameter 750 to 780 with a depth of 0.4 to 0.43. And we have one positional tolerance, one feature control frame. So we have one positional error, positional tolerance zone of 5 thou at maximum material condition. Okay, so what this looks like is we have a tolerance zone, and this blue bar right here is the tolerance zone. And you can see I've shown on the right-hand side that it is a circular or cylindrical tolerance zone, right? Because we have a diameter symbol, so it's a cylindrical tolerance zone. The center of the primary hole and the center of the counterbore hole must lie within that tolerance zone. So the red line there is the center of the primary hole. And the red line there is the center of the counterbore hole. And I'm purposely showing the center of the counterbore can be off or away from the center of the primary hole or the through hole. Okay? So we can have that kind of discrepancy as long as both centers lie within this, in this case, 5 thou tolerance zone at MMC. All right, so let's move on to method number 2, separate positional tolerances for the hole and the counterboard. So look how this changes, right? So now we have a feature control frame for the holes and a feature control frame for the counterboard holes. All right. Notice that we have different tolerance values here. So in the primary hole, the through hole, we have a 5 thou tolerance zone. In the counterbore hole, we have a 20 thou tolerance zone. Typically, the counterbore tolerance is going to be larger. 20 is larger than 5. Typically, you want that to be the case. Okay? Because the counterbore is going to be less functionally important as the main hole. All right? So what this looks like is, well, we have the tolerance zone for the 5 thou, but now notice the tolerance zone stops. It's only as long as the primary hole. Let's go back a second here. Notice on this, the tolerance zone extends through both holes. Here, it only goes through the hole that it is applied to. The axis of that hole must lie within that allowable tolerance zone. And then we have a second tolerance zone. In this case, it's larger, 20 thou versus 5 thou. And the center of the counterbore must lie within that larger tolerance zone. Holes are still free to move in opposite directions. Finally, the third method is a little bit, kind of out there. I guess the main purpose of showing you this, it's discussed in your book, but the main point of showing you this is that it is possible. And that's one of the benefits of geometric dimensioning and tolerances. You can make it say exactly what you want or what you needed to say functionally, the geometric tolerances. Okay? So in this case, the counterbored position is referenced to the hole location. So what is the difference here? Well, we still have two feature control frames, one applying to the primary or through holes. But then the second one, I want you to notice the difference here. Notice the datum reference frame. Here we have ABC. In the second feature control frame, we only have D at maximum material boundary. And where is D? D is the feature, is a datum feature of size on the primary or through hole. So that's the axis. So this one links the center of the tolerance zone on the counterbores to the center of the tolerance zone in the primary holes. So in this case, the tolerance zones are linked. It's centered on the primary hole axis. All right. Let me go back here. You'll notice in this one that it's still ABM. Both of them are ABM. And even in this one, when we go back, this is just ABM, right? So here we have two separate datum reference frames. So the tolerance zone here, this is the 22 thou tolerance zone. And then this is the axis of the primary hole. And then the tolerance zone for the counterbore hole is going to be centered on that axis. And then it's going to be, in this case, 10 thou. Okay. All right. So those are the three methods for dealing with positional tolerance and counterbored holes. If it's not a big deal, if you don't need to really control the tolerance zone for the counterbored hole, if you don't need to, if you have enough clearance in your counterbore, which usually you would do, then you would, by all means, use method 1. Method 2 would be used if this tolerance, see how restrictive this is? This is 5 thou. If you're thinking, well, why the heck would I want a 5 thou tolerance on a counterbore that really isn't that functionally important? Then you go with this one, right? Method number 2. So now we've opened up this tolerance. And basically, when you open up a tolerance, that means you're rejecting less parts. Because remember, if a part does not meet the tolerance specification, it either needs to be sent back to the machine shop for rework or it needs to be scrapped. Both of those are very expensive propositions. So it behooves you to make the tolerances as large as possible so that the machine still functions. All right. So moving along, and I'm going to do an example of this. Projected tolerance zone is very useful. All right. This is where we can take our tolerance zone, which normally extends only through the length of the feature. So in this case, this tolerance zone, 0.018, if we didn't have the projected tolerance, the circle P, forget the circle P right now, the 0.018 tolerance zone would only be as long as this hole is right there. But sometimes we want the tolerance zone to extend outside the boundaries of the feature. When we do that, we use the circle P, that means projected tolerance zone, and then we include the amount that we want to extend it. So in this case, the circle P with a 0.5, half an inch, means that we're extending the tolerance zone half inch above the feature. So the tolerance zone, in essence, goes from here, the bottom, all the way up to the top and past it by a half inch. Okay? So that is the projected tolerance zone. Last couple of slides here on bidirectional tolerance, positional tolerance. So this is an interesting application. So we have a slot, right? And obviously for a slot, we don't want a cylindrical tolerance zone because the slot is not cylindrical. It has a rectangular element and it has a rounded element or features. So if we apply the positional tolerance like this, where we're applying one positional tolerance to the width dimension and the other positional tolerance to the length dimension, and notice in both cases that we are omitting the diameter symbol here because we don't want a cylindrical feature of size. We want the feature of size to match the geometry. What this is going to create is a tolerance zone that has different width and lengths. So in this case, the 14 thou tolerance zone creates a width of 14 thou. And the 60 thou tolerance creates a length of 60 thou. So we have a rectangular tolerance zone. Right? Okay? So we can also see this here. We're applying the tolerance zone, the feature control frame, to the length here, 1.5 millimeters at maximum material condition, and to the width, 0.5 millimeters at maximum material condition. And so this is what we're creating. We're creating a tolerance zone that is rectangular. All right. So it's pretty neat. Again, the idea here is that we can customize our geometric tolerancing to fit the functional requirements of our parts. And that is the great benefit here. Otherwise, with just size tolerances, we would not be able to do this, or it would be extremely difficult to do this. All right, the last couple things we're going to look at are non-cylindrical features of size, right? So we've been focusing really on holes, mostly holes, a little bit of cylinders. But we can, of course, control the position of non-cylindrical features of size. So in this case, we're looking at a slot or a notch, right? And we have we deal with it the same way. So just imagine that this was a hole, right? So you apply the feature control frame to the size dimension, just like we do for the hole. In this case, it's a rectangular hole or a square hole. So the size tolerance is 2 inches to 2.002 inches. And then we have the positional tolerance of 10 thou at MMC, which creates a tolerance zone that is 2 parallel plates that are fixed in location at the MMC, or excuse me, at the basic location of this slot. And you can see that here. This is the tolerance zone. They're showing you the tolerance zone here. This line right here is the center plane for the produced feature. All right. So remember that what we're trying to show you is the drawing, the perfect feature, and then how the produced feature, the manufactured feature, can acceptably be positioned and still be a good feature. Okay. Of course, one great application for this is with key seats in shafts. And so I'm sorry for the blurriness. I enlarged this so that everybody could see this a little bit easier, but it got pixelated a little bit because of the resolution issues. But this is a great application of using positional tolerance, right? Again, we do not include the diameter symbol because this is not a cylindrical feature of size. This is a square or rectangular feature of size. All right. So in this case, this is a clearance fit, right? Circle M means it's a clearance fit. Same thing back here. This is a clearance fit. Circle M means a clearance fit. Okay. All right. So that concludes part number 2 of chapter 8. I will now, I'm going to upload this and then I'll upload another video with another practice problem. All right. So talk to you soon.